general relativity step by step. Last time I derived these Lorentz transforms and I was waxing lyrical about how wonderful they were. Now I'm going to start using them. I'm going to make a slight change of notation. Before we had t and x and t bar and x bar. Now I'm just going to call that x0 and x1. And I'm going to call it x bar 0 and x bar 1. Sometimes I'll write x bar 0 and sometimes I write x0 bar. I'm never quite sure which is the better way to do it. I blow hot and cold on it. Okay, so let's just have a look at the transform here in this notation. I know I'm not doing anything clever here, but you'll see why I'm doing it in a minute. We've got x bar 0 equals, well, it's from up here, isn't it? It's all I'm going to do is write down, so it's gamma t plus gamma beta x. So it's gamma x0 plus gamma beta x1. And x bar 1 equals gamma beta x1 plus beta, oh no, that's a 0, x1. So all I'm doing basically is writing out this matrix in its transformation rules. Okay, well that's great. That's nothing very spectacular, but watch. Now I can start to do this. Die x bar 0 by die x0 equals, well, it's this term here, gamma. And what else have I got? I've got die x bar 0 by die x1 equals gamma beta. And now I've got die x bar 1 by die x0 equals this term here, gamma beta. And die x bar 1 die x1 equals beta. That might not look like a terribly intelligent or difficult thing to do, but it's quite profound, and it's oops, I don't quite know what happened there. Oh, it's up here. It's quite profound. The reason I can do that, and the reason it's nice and simple, is that the Lorentz transformation matrix, gamma, gamma, beta, gamma, beta, gamma, it's a linear transformation. There's no coordinate dependence here. There's no t here. There could be an x to the minus 3 there. There could be all sorts of weird coordinate dependence, but there isn't. The Lorentz transformation, they're just numbers. Of course, beta equals v over c. It's just a constant. And gamma equals 1 over root 1 minus beta squared. It's just a constant. It's just a feature of the... they're just functions of the relative speed. Well, this is great. Now... well, why do I want to do that? Well, you'll remember from screencast, I don't know, 3, 4, right at the very, very, very beginning, I gave you the transformation law for a contravariant vector, which was this, v alpha bar equals, you remember I got my sort of formula for working this out, dix v. That's upstairs, that's going to be upstairs. That beta needs to contract with a beta here. This has got no bar on it, so that's got no bar on it. There's a free index alpha there, which must match this one here. That's got a bar on it, so that's got a bar on it. This is for any contravariant vector. Okay, so I can say that v bar 0 equals die x bar 0 by die x1 v1 plus die x bar 0 by die x, oh no, I should start at 0, 0, 0, 1 v1, which equals, but now I can just substitute these differential forms here, these differentials here, from my calculations here. So I can just do that. Die x bar 0 by die x0 is just gamma. So it's just gamma v0 plus this term here, gamma beta v1. And of course, I can say that v bar 1 equals gamma beta, just purely analogously, v0 plus gamma v1 for any contravariant vector. And what I'm going to do is to show you what kind of contravariant vectors we can deal with. But now we can transform between them quite easily, according to the Lorentz transforms. So I'm going to stop there. Stop.